Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is production of X-rays. In the year 1895, Wilhelm Conrad Röntgen accidentally discovered X-rays while performing experiments on cathode rays. The electromagnetic nature of X-rays were soon understood after their initial discovery. The X-rays were found to be highly penetrating radiation of unknown origin originally. They were produced when fast moving electrons impinge on matter. They had high penetrating power. They traveled in straight lines, and X-rays were not affected by electric or magnetic fields. X-rays caused phosphorescent materials to glow, and they were found to expose photographic plates. The faster the electrons impinge on the target material, the more penetrating the resulting X-rays were and the higher their intensities. Scientists struggled for over a decade to measure the X-ray wavelengths. It was clear that X-rays were unlike light in the sense that their wavelengths were shorter and hence they were not diffracted by the optical gratings, plane optical gratings. And due to the other properties that we've mentioned already, it was clear that the X-rays must be having wavelengths shorter than the visible light. It was Max von Laue in the year 1912 who proposed that X-rays could be diffracted using crystals. Röntgen was awarded the 1902 Nobel Prize in Physics, the first Nobel Prize in Physics in the year 1902, and Max von Laue was given Nobel Prize for his discovery of diffraction of X-rays by crystals in the year 1914. The medical applications of X-rays were realized very soon, in fact within months after their initial discovery. But the discovery by Max von Laue led to several other applications for X-rays in the following years after 1912. The initial wavelengths that were measured following Max von Laue's experiments for X-rays were in the range of 0.013 nanometers to 0.048 nanometers. But X-rays are now known to have wavelengths spanning a wider range of 0.01 nanometers to about 10 nanometers at least. The numbers on either side of this range are not very rigid in the sense that the lower wavelengths overlap with the wavelengths of the gamma rays and the higher wavelengths overlap with the wavelengths of the ultraviolet rays. But these numbers give an idea as to what sort of wavelengths we are dealing with and why it is difficult to diffract X-rays with the plane optical gratings. Plane optical gratings have a number of closely spaced lines engraved on typically glass plates that causes visible light to get diffracted, whereas the shorter wavelengths of X-rays require that these lines in a grating be much closer than there. Then it is possible to engrave them on an optical grating. And that is the reason why plain optical gratings cannot be used for X-ray diffraction. Max von Laue was able to figure out that the spacing between atoms in crystals typically is of the order of the possible wavelengths of X-rays that is suspected to have, and hence he proposed that crystals could be used to diffract X-rays. We'll discuss the X-ray diffraction in a separate video, but the focus of this video is on the production of X-rays. So let us get into some details on the production of X-rays. The schematic diagram of the experimental setup used to produce X-rays is shown here. This is the schematic of a typical X-ray tube. This is an evacuated glass tube, typically made of borosilicate glasses such as Pyrex or Mg. We have a couple of electrodes in this tube. We have anode, which is a metal target, and we have a cathode behind which an electron gun produces electrons by thermionic emission uh, due to a potential that is applied across its two ends, and a larger potential is applied across the anode and the cathode so that the electrons that are produced here are made to move fast towards the anode and strike the anode, and this results in the production of X-rays. The tube is evacuated so that the electrons are not disturbed in their paths during their journey from the cathode towards the anode. Cooling arrangements are made within this tube so that the anode, which produces a lot of heat, the heat that is produced at the anode is dissipated quickly. Now let us get into some details of the mechanism of production of X-rays. Classical electromagnetic theory predicts that accelerated charges produce electromagnetic radiation. Here we have the electrons as the accelerated charges, and when these electrons are stopped by the anode, or when they strike the anode at very high velocities, they are decelerated. And this should result in production of X-rays because either accelerated or decelerated charges can produce electromagnetic radiation, which can be proved using Maxwell's equations. There is a term that describes the production of X-rays by this process, and that is called Bremsstrahlung, and this simply means breaking radiation. Brakes are applied on the rapidly moving electrons, and the electrons are stopped, and a radiation results from this, and that's why the resulting radiation, that is X-ray radiation, that results here, which can be collected using some kind of a window in the tube, such as beryllium window, for example, and these X-rays can be further processed and analyzed and used for various applications. So in the X-ray tube, a charged particle that is accelerated results in the production of X-rays, and the kinetic energy of the rapidly moving electrons is converted into the energy of the X-rays. The actual process involves the fast moving electron interacting with, let us say, a nucleus of an atom in the target material, and this electron typically gets decelerated and it transfers its energy, and this resulting energy is emitted as X-rays. So typically, the target material that is used should be a high melting material. That is a material that has high melting point because of the heat that is generated. It should also have a high atomic number, let's say Z. It is easy to see that the X-ray production process is the inverse of the photoelectric effect. In the photoelectric effect, we have a target metal surface on which light is incident, and the energy of the photons is getting converted into kinetic energy of the electrons that are ejected from metal surface. On the other hand, in the X-ray production, we have a target metal surface on which rapidly moving electrons strike, and the kinetic energy of the electron is getting converted to X-ray photons, which are basically light photons. So one can see that the X-ray production is basically the inverse of the photoelectric effect. Now, typically in an X-ray tube, a large number of electrons strike the anode, and only a tiny fraction of the electrons help produce X-rays, or only a tiny fraction of the electrons uh, result in production of X-rays. Much of the electrons that strike the anode, uh, their energy is wasted as heat. So cooling mechanisms are in place within the X-ray tube to ensure that the anode does not melt, and the heat that is produced is efficiently dissipated in the process. Classical electromagnetic theory of Maxwell is able to explain the production of X-rays via the process of brainstorming. But if you observe the X-ray spectrum, there are a few things that cannot be explained classically. We need to use quantum mechanics to understand those things. Let us get into those details now. A typical X-ray spectrum looks something like this. We have the wavelengths of the X-rays that are produced in this experiment along the x-axis, and the relative intensities of the X-rays along the y-axis. For different applied potential difference between the anode and the cathode, we have the variation of the intensities as a function of wavelength plotted here. For 25 kilovolts, for 30 kilovolts, 35 kilovolts here. And let's say this is for a target material tungsten. The anode is tungsten in this case. This is called as a continuous X-ray spectrum or continuous X-rays. The X-rays that are produced via the process of Brainstorm, they are typically called as the continuous X-rays, because you have X-rays over all wavelengths, starting from a lower wavelength to higher wavelengths, and as the potential difference is increased, we have X-rays of higher and higher intensities. And what is interesting in this is that we have the lowest wavelength for each of this applied potential difference shifting towards the lower and lower end of the wavelength axis. That is, the lambda minimum for a given potential shifts towards left as the potential is increased. This is not explained. This cannot be explained by classical ideas. One has to understand that the X-ray production is basically inverse photoelectric effect, and therefore one has to use what is called as a photoelectric equation to understand this. We'll come back to that in a moment. On the right hand side, we have plotted again the same X-ray spectrum, but in this case the target materials are different. So we have the spectrum here on the top for tungsten, and the spectrum for this one is of molybdenum, which is the target material in this case. And we see some spikes in the spectrum at certain wavelengths, and this cannot be explained again classically. One has to understand that this happens due to the electron structure rearrangement in the target material, the electrons shifting between different shells, and And therefore, one has to understand using quantum mechanics the complete atomic structure of the target material to answer as to why we get spikes at specific wavelengths. And these spikes are due to what are called as the characteristic X-rays. So the overall spectrum is continuous X-rays, and the spikes are due to what are called characteristic X-rays. So basically there are two types of X-rays that are produced: continuous X-rays and characteristic X-rays. Continuous X-rays can be, the production of continuous X-rays can be explained using classical ideas, using Maxwell's electromagnetic theory, using Maxwell's equations. Whereas the production of the characteristic X-rays cannot be explained classically. One needs to use quantum mechanics to understand and explain the production of characteristic X-rays. Similarly, on this curve, the wavelength, minimum wavelength dependence on the applied potential difference between anode and the cathode also cannot be explained classically. So let us get into that part of the discussion now. As I already mentioned, X-ray production can be understood as the inverse of the photoelectric effect. Therefore, we have to use the photoelectric equation to understand uh, the shifting of the minimum wavelengths towards the lower end of the axis here. So let us start with the photoelectric equation. The energy of the incident photon in photoelectric equation is equal to the kinetic energy of the electron plus the work function of the material or the metal surface that is used in the case of the photoelectric effect. For X-rays, the potential difference between the anode and the cathode is few tenths of kilovolts. The work function for most metals is in the range of a few volts, and therefore this can be ignored because of the differences in the ranges. And therefore we can rewrite this equation here in this case as the kinetic energy of the electron is getting converted to the energy of the X-ray photons, and this frequency is the maximum frequency, because if the entire energy of the incoming electron is converted into the X-rays, then it is completely going to result in the energy of the X-ray photons, and therefore the frequency has got to be maximum in that case. But typically one would imagine that the incoming electrons would face more than one atom or more than one nucleus in the process, and gradually it would slow down. So the maximum possible kinetic energy, the maximum possible photon energy is going to be entirely the kinetic energy of the incoming electron. In that case, one would say that this equation is valid, and one can write that the kinetic energy of the electron, which travels between a potential difference of V, capital V, let's say, is EV, where E is the charge of the electron, and therefore this can be written again in terms of wavelength as hc over lambda minimum, because when frequency is maximum, the wavelength has got to be minimum. And we can write now that the lambda minimum therefore is equal to hc over ev. And if you work out these numbers, there is a Planck's constant h, the speed of light c, and the charge of the electron e, keeping the potential difference as v, then we would get lambda minimum is equal to 1.24 into 10 power minus 6 over the potential difference v meters. Actually, we have a unit of voltmeter here because this will be expressed in volts. Then this will result in this number. And this relationship between the minimum wavelength and the potential difference was proposed by Duane and Hunt. So this formula goes by the name Duane-Hunt rule, and that explains the peculiar observation in the X-ray spectrum of the dependence of the minimum wavelength on the applied potential difference between the anode and the cathode. And thus we can clearly see that based on these arguments, the X-ray production is basically nothing but the inverse photoelectric effect. That brings us to the end of this video. Hope to catch up with you soon on another interesting video. Until then, it's bye from me. Thank you.